Hello everyone. This is Palak Jeetwani, and today we are going to discuss on the topic artificial neural network. Now it's a very vast topic, so obviously we are not going to discuss everything. Uh, we'll have an introductory session and also going to discuss the back propagation algorithm. So we sh- uh, you should not get intimidated by this word artificial neural network. It's not that complex as it appears. We are going to make it very easy by interrelating everything in the artificial neural network with the human brain. So before we begin, we'll discuss one example. So as you can see in this slide, there is this person who's touching a hot object. And the moment he's touching this hot object, the response that is generated is his hand is taken away. So what happens is, for example, this is the hot vessel. Okay. The moment I touch this hot vessel, what happens is my skin, my hands, being the sense organ, they sense the temperature. The sensory responses are then sent to my brain. The neurons receive it, and finally, the muscle contracts, and a motor response is generated, and my hand is taken up. So this is what is happening. This person is touching this candle, and the signals are going to his brain by this efferent neuron, and the efferent neuron is finally giving the motor signals, and the hand is taken up. So now, why did we discuss this example? Similar things, because similar things happen in the artificial neural network. What happens is, like this, the vessel I touch, okay, this can be taken as the input for my artificial neural network, or in like which equivalent to the human brain. So I touch, okay, I sense the hotness. The input is taken by the artificial neural network, and in place of the neurons, the artificial neural network has nodes, or I can say perceptron. Okay, so like the neurons are the basic function unit of our human brain. Everything like we say the sense organ took the impulses to our brain, but where it actually took the impulses to the neurons present in the human brain. So similarly, the inputs that are collected, that whatever input I have collected, that reaches to the nodes of the artificial neural network. And finally, like in the human brain, the motor response is generated when my hand got pulled away. Similarly, the node generates an output function. Okay. Now, output function is basically according to the inputs that the model has received. So everything is quite similar. So, like if I look at this diagram of neuron, the neuron has three broader parts: the dendrites, which receive information, the body of the neuron, and the axon, which transfers the information to the other neuron. Okay. So, what is an artificial neural network? I've already told you all these things. Human brain consists of millions of neurons. Neurons are the fundamental unit of the brain. Natural functions are done artificially by artificial neural network. So, what naturally our human brain is doing is what we have done through the artificial neural network. So, biologically known as neurons, artificially known as nodes. Now, brain versus ANN, again, we have discussed. This is a diagram of the node. Like we saw the diagram of neuron having three parts. Similarly, we have this diagram of node. Now, the node has two major parts: the summation function or the transfer function, and the activation function. Now, what is happening? For example, like my model gets n number of inputs. Okay, now my model has got n number of inputs. My model needs to know which input is important for me and which input is not that important for me. So every input that the model receives is attached with its corresponding weight. Like for example, X1 is attached with W1, X2 is attached with W2, and X3 is attached with W3, and so on. So every input has its own importance. Now, importance is labeled as weights. Okay, so you can see over here, there are n inputs being provided to the model, and with its corresponding weights: W1, W2, W3, and W1. Now, all these inputs and weights, like X1 is multiplied with W1 with its importance, X2 with W2, all these are multiplied and added together, and a summed up net input is calculated through the transfer or the summation function. Okay, so X1 into W1 plus X2 into W2 plus X3 into W3, and so on till Xn into W1. So we have calculated the summed up input of all the inputs along with their weights. Now this input goes to the activation function. Now activation function basically segregates the important part, okay, and it generates the output based on the important input. So an output is generated by our model. Now basically this output generated is calculated by the expected output. Okay. So like whatever the error is, that we rectify using the back propagation algorithm, which we'll discuss further. So this is the major two components of the node. So in this slide, the same thing is mentioned. A node has two parts: summation transfer function, activation function. And x1, x2 are input functions. W are the corresponding weights of the input functions. Okay. And see, these input signals along with the corresponding weights reach the transfer function, summation function, where the weighted sum of the inputs are calculated. And this net input function is then sent to the activation function. Activation function generates the output based on the inputs. As I already told, all these things are written over here. Okay. Now, as we all know, in the human brain does not have one neuron, right? Like example, the information which was sent, like the hot vessel I touched, the sensory neuron which received the information, then passed on the information to the motor neuron, which then resulted into a motor response, and my hand got away. Similarly, the artificial neural network is not comprised of a single node. It is a combination of nodes. Now there is a certain representation of how the nodes are going to be assembled. For example, in the case of human brain, the neurons are connected end to end, like to create a synapse, a junction, so that one axon can send the signal to the other dendron. Similarly, here the case is there are three layers. The nodes are segregated in three layers: input layer, hidden layer, and output layer. As we can see, there are three distinguishable layers. Okay. Now there is certain rule to arrange these nodes. How? First of all, there can be any number of nodes present in all the layers. Like whatever your requirement is, you can put as many inputs as you want to. Sorry, nodes as you want to. But a thing to observe is that every node in the previous layer, right? For example, this is the previous layer, input layer. This one is the previous layer for this layer, right? This one. So every node in the previous layer is connected to all the nodes in the next layer. Like if we see the node refractive index of core, it is connected to all the nodes of the first layer, first hidden layer. Like NC is connected to H1, NC is connected to H2, and NC is connected to H50. Like till 50, every node it is connected to. And you can observe this thing at every layer. Like if I go to layer 3 and take this H1, H1 is connected to the effective index, H1 is connected to the effective mode area, H1 is connected to the dispersion, and H1 is connected to the confinement loss. Means every node in the previous layer is connected to all the nodes in the next layer, because we want the inputs, we want the weights, because these edges, all these edges have this particular weights. So we want the output to be summed up by evaluating all the weights, all the inputs. So that is the reason it goes to every node. So this was the basic representation. The things I mentioned are written over here. ANN is divided into three layers: input layer, middle layer, and outer layer. Input layer is basically acting as a receiver. All the inputs are being received by that layer. Middle layer's work is to segregate what information is important and what information is not important. Okay, so the extraction or the segregation of the relevant data, because our output does not want every input to be there. Okay, output of the model is only generated based on the relevant data. So the middle layer functions in extracting the relevant data, and outer layer producing or presenting the output to the user, like in user interactive output. Any number of nodes can be present in each layer. Based on the input we are taking, the nodes may vary. So any number of inputs can be present, nodes can be present in each layer. Every node in a given layer should be connected to all the nodes of the next layer, as we have already discussed. Okay. Now, appropriate problems of neural network. We are not going to like discuss every problem because it will take too much time, but we can just discuss situations where it can be useful. Okay. So first situation is instances have many attributes or value pairs. Now, if we look into decision tree learning method, it fails when there are a lot of attributes or value pairs, a lot of training sets. But in the case of ANN, this is possible. Second is training example with errors or missing values. So when there are certain errors, there are certain missing values in the training data set, then also it is functional. Long training times are acceptable. Obviously, the model may take time to generate the output function, but the evaluation of the target function learned is faster. I'm so sorry the slides were not changing. I'll go through it like in a quick way once again. Okay. So yeah. So I think this example was very much clear. What I tried to make you all understand. Like I think I don't have to repeat this example again. Okay, we'll start with the diagram of node. Okay. So yes, as I already discussed, the neuron has three major part. Okay, the dendrons, the body of the neuron, and the axons. Okay. Similarly, the nodes have two important parts. Okay, the first is the transfer function. Second is the activation function. Um, Now, what is happening? Like, for example, I provide my model with some inputs. Okay, with like n number of inputs. Now it's I have to decide like which input has what importance. Okay, so every input is associated with its importance, that is the weights. Okay, and the transfer function is going to calculate the summation of all the inputs along with the weights. So the net input is generated and the activation function hence gives you the final output. So I think we first went through this example which I try to relate with the human brain. I hope that is clear. Then we went through the two major parts of the nodes, which is the summation and the activation function. Okay, I'll begin from here. The representation of artificial neural network. So as I was explaining, there are three major layers in the artificial neural network: the input layer, the hidden layer, and the output layer. Okay, so um, we can like majorly divide it into three parts: the input layer, hidden layer, and the output layer. Now, as we all know, in the human brain, there is not one neuron present, right? A human brain is a combination of lot of neurons. Okay. So one neuron is present, the axon of one neuron is connected with the dendrons of the other neuron, and a synaptical junction is created. And that is how the information from one neuron is transferred to the other neuron. So similarly, in the artificial neural network, it is not consisting of single node. It is consisting of uh, a lot of nodes. Okay. So this is basically the representation of how the nodes are present. So there are certain rules for the arrangement of these nodes. Like in the case of human brain, the neurons are connected end to end. Similarly, in the case of artificial neural network, the nodes, like I already told you, the every node in all the layers are connected to all the nodes of the next layer. So now you can, I hope you can see the slides. The refractive index of core, this NC node, is connected to all the nodes of the other layer. Like it is connected to H1, it is connected to H2, it is connected to H50. Similarly, if we see the wavelength node, it is connected to H1, it is connected to H2, and it is connected till H50. So this is the rule for arranging our nodes. That is, every node of a layer, previous layer, is connected to all the nodes of the next layer. So now I think it is very clear through this slide. So this is what is mentioned over here. ANN is divided into three layers: input layer, middle layer, and outer layer. Any number of nodes can be present in each layer. Based on the input we are taking, the nodes may vary. Every node in a given layer should be connected to all the nodes of the next. Now, appropriate problems of neural network. Obviously, we are not going to discuss all the problems because like we are just focusing on the basics of artificial neural network and the back propagation algorithm. But we can discuss the situations in which we can use the ANN. So first is instances have many attributes or value pairs. Now, when there is a huge amount of data set, okay, training data set. So what happens is decision tree learning usually fails in this situation. But ANN are preferred as they can handle all these large number of data sets and can give you appropriate outcomes. Training examples with errors or missing values. Now we have when we have data set which has certain missing values or errors, then also this can work. Long training times are acceptable, and faster evaluation of target function learned. The evaluation of the target function that is learned is quite fast. This was not that important. Okay, now we move on to the perceptron. Um, so perceptron, as I already told you, is the other name for the node. We can I mean, say the basic functional unit of the ANN as node or perceptron, anything. So this is a diagram we have already discussed, the transfer function and the activation function. So basic unit to build ANN, take real value inputs, continuous inputs it's going to take like x1, x2, x3, xn, along with their importance weights, calculate the linear combination of these inputs. So as we have already discussed, these weights along with the inputs go to the transfer, the summation function. And finally, the net input is calculated and the activation function is going to give you a output. Now, what is happening is when we design a model, okay, the model that is designed has a specified output, okay, which is the target output we have to reach. So, for example, this like consider this diagram has some values, okay. So the target output is 0 0.8, for example, and what I am getting, the output that I am getting, actual output of my model is 0 0.5. Okay. So the target output and the output which my model got are not same. So I need to rectify those errors so that my model can work efficiently. Because at the end, what is my sole purpose is to make the target and the actual output equal. Then only my model is efficient. So there are two major notations which we are going to use in further calculation is O, which is the actual output, which on calculation and on doing all these things, our model gives. And T is the target output. That is the output which actually was expected that my model should give this. Now, if these two are equal, obviously my model is 100% efficient. If these are not equal, I have to rectify the errors. Now, how to rectify the errors, we are going to see in further slides. So now I know like my model has some errors, like T is not equals to O. Now, if like I ask you all, like where is the error coming? Like what is one thing which I can change to make my model efficient? I think it is the weights. So what is happening is when my model is generating a output, is it is generating output based on the inputs along with its importance. Like X1 had some W1 importance, X2 had some W2 importance, and I summed up all those inputs along with their weights and calculated the output. Now, what is the problem is my weights are not correct. What importance I have given to all the inputs is not correct. That is the reason the output I'm getting is not correct, right? So I need to change the weights. I need to change all my weights of the specified input so that I can get my desired output. Now, how do I change these weights? Changing these weights is actually done with this formula. Like the weight can be changed by adding delta W to it. What is delta W? That is eta times T minus O into Xi. Now, what is eta? Eta is the learning rate of your model. T is the target output, that what I expected to get, and O is the output that I got through my model. And what is Xi? Xi is the corresponding input with the weights I am changing. So I have to change all my weights because my the output I received is not correct. That is the reason I have to change all my weights. So this procedure, this step has to be followed for all the weights. But isn't it too tiresome? Like I keep iterating all my weights and checking, uh, like is this weight correct or not? Like if I change all my weights and calculated the output, and again it is not equals to the target output, then again I have to change my weights. So I need something which can give me the value of the weight which is appropriate for my model. And I'm sure that this weight, if I put, that is going to give me the right answer. So that is how we proceed towards the gradient descent algorithm. The gradient descent algorithm basically works in calculating the weight which can give you the desired output. So this was the perceptron training rule, which was used for linearly separable data, what we saw previously. And now we are going to see the delta rule. It's going to use for the non-linear separable data. These two terms are linearly separable data is like, for example, in the first image, we can see there is red dots and blue squares. These two can be separated through a straight line. Linear means straight line. So I can separate these two data sets with a straight line, right? So this is linear separable data. And when I cannot draw definite straight line to segregate my data, that is when it is called as non-linear separable data. Like in this image, I cannot separate my data with a straight line. There is still these two data which are being interrelated. And similar thing is happening over here. Okay. So yes, now our idea was to calculate the weight, which can give us the appropriate um, target output. Okay, sorry, the output which is equals to the target output, right? So how do I do that? So we use the concept called as cost function. Now, cost function for any algorithm, be it linear regression algorithm, logistic regression, anything, the cost function is always same. What is the cost function? Cost function is 1 by 2 multiplied by t minus o whole square. T is again the target value. O is the output we have got through a model and whole square. So this is the cost function. Now, what happened was when I plotted the cost function for different weights, like I plotted cost function by taking different weights. So on y-axis, as you can see, this is the cost function. On x-axis, you can see the weight. So the plot, when the dots were joined, it came out to be a U-shaped plot. Okay, it came out to be a U-shaped plot. And when the weights of these cost functions were considered and were put into the equation, it was found out that the point at which the cost function is minimized, the weight corresponding to the point where the cost function is minimized is the weight which we actually desire. By keeping this weight, my model is working 100% efficiency. So how do I get this weight? Like if we like in maths, when we see any U-shaped curve, when we have to calculate the minima of any curve, we differentiate the function with respect to the x-axis. Dy by dx should be equals to 0. That is the minimum. So that is how we are going to calculate the minima over here, which is actually the concept of gradient descent. That is when we plotted the cost function with the corresponding weight, we got a U-shaped curve, and we found out that the minimum cost function was at a particular weight. So how to find that particular weight is through the gradient descent algorithm. So same thing is written over here. So gradient descent algorithm is, gradient means to take the gradient, that is the gradient function we have studied, and descent is the small incremental steps. Like we can see small steps are going to reach till the minimum cost function. So main idea of the delta rule is uses gradient descent rule and finds the best weight. In machine learning, cost functions are used to estimate how successfully models are performing, and the cost functions half of the difference between the predicted and the accurate value. The error keeps on decreasing with the change of weight. That is, we have to calculate the minimum of the cost function, which hence is the appropriate weight to best fit in. This is done with the help of gradient descent algorithm, as we have already discussed. Now, how do we use this gradient descent algorithm in calculating delta W? Ultimately, we have to change our weights. We have to add something to our weight so that our weights can be modified. So descent means decreasing. That is, the error keeps on decreasing. As we can see, as it goes down, the error keeps on decreasing. Error is nothing but the cost function. The point where the minimum error occurs, the weight should be noted and not changed further. How to modify the weights? The same formula, perceptron training is used. The same thing is used. Wi is changed by adding delta W to it. So yes, now the formula changes. Delta W, which was previously this, now changes to minus eta del J by del Wj. Now, J over here is the cost function. So we are going to differentiate the cost function with the corresponding weight, and hence going to get the delta W, the added value to our weights. So see, del J by del Wj is the derivative of the cost function with respect to weight, known as gradient. This term is known as gradient. Eta, we have already discussed, is the learning rate. And the weights are then updated by the following rule. Okay. Now, this is little mathematics. So if we see del J by del, now we have to calculate basically this. We are actually modifying one weight, and we are calculating delta W. So del J by del W naught, if I put J over here, this J shouldn't be over here. So del by del W naught, that is, the value of J was half into T minus O whole square. Now, what is this small d and d over here? Now, let's see. Like we have discussed, we had certain inputs, x1, x2, x3, x4, and so on. Now, every input data set has some training examples. Like, for example, the x1 input has some capital D over here, number of training examples. So I have chosen one training example. Small d over here signifies one training example. So one training example belongs to the capital D, entire set of training example of one input, which is corresponding with this W naught, one weight. So this TD, this is one training example minus OD, the output obtained of that particular training example, whole square, where D belongs to capital D, that is entire set of training example. They are summed up, and then this is calculated. So this is WI means it is generalized. Now, firstly, we are calculating for the first weight. Now we are generalizing. So del of this function upon del Wi. So basically, this is differentiation. How do I do that? So if a raised to the power n has to be differentiated, what will be the answer? N, a raised to the power n minus 1. So similarly over here, it will be half will remain as it is. Then 2 will come over here. The square comes over here. TD minus OD, 2 minus 1. So 2 minus 1 is 1. And by chain rule, we are going to again go inside this. So del by del Wi, TD minus OD. Right? So this 2 gets cancelled. This is TD minus OD. Now again, we have to differentiate. Okay. Now what is the output? Output was initially when we saw what was the output we were getting. For everything, the output was O1 is equals to X1 W1. So similarly, over here, I can replace OD as WD into XD, the input along with the corresponding weight. So now when I differentiate it with W, this TD term becomes constant. So it is 0 and minus WD XD. So we are differentiating with respect to W, hence XD comes out, minus XD. So what the result is? The summation of TD minus OD and minus XD because of this. Okay, so this is what the del J by del Wi value was there. Now we have to put it in delta Wj because finally we have to calculate the modified value of W. So delta Wj is what? Minus eta times del J by del Wi. So minus eta times this value, which is equal to delta Wj eta times Td minus Od into Xd. This minus minus, already there was minus, and this minus Xd, so minus minus get cancelled, and finally we get this. So this was us calculating the delta Wj value. Now we'll move on to the multi-layer neural network. Now what happens is, we have tried to rectify the output. Like we know that every model has a target output, and every model generates its own output called as capital O. So now in moving in the forward direction, we have rectified the errors. We have tried to rectify the errors through this delta rule, and we have tried to bring our the output we have got to equals to the desired output, that is the target output. Now, if I want to rectify my, like for example, when I move in this direction towards my outer layer, I want to rectify my errors by moving backwards. This can be done when I use two hidden layers. So this is what multi-layer neural networks are. It is very similar to what artificial neural network is. Only the only difference is there are two hidden layers. So what is the need of multi-layer neural network? A single layer neural network is only going to work for linearly separable data. Very important. Like if I choose only one hidden layer, it is only going to work for linearly separable data, which we have already seen over here. Linearly separable data, which we can separate through a straight line. But when we work for non-linearly separable data, we have to use multi-layer neural network. The only difference between the two is that the multi-layer neural network has two hidden layers, where the single layer only had one hidden layer. Where single layer neural network we discussed only had one layer. And this over here, as you can see, it has two layers, layer 1 and layer 2, the green one and the orange. The same rule is applied that every node of each layer is connected to each and every node of the next layer. That representation, the arrangement is similar. Like every node over here, like the blue box, the dark blue box over here is connected to all the green dots of the next layer, and all the green dots are connected to all the orange dots of the next layer. So the arrangement is similar. And what is the advantage? We can use the backpropagation algorithm. So for non-linearly separable data, we have to use this multi-layer neural network. Basically, backpropagation is allowed, which will be discussed further, that we can go backwards and rectify the errors. So there'll be two outputs. Like not necessarily every time there'll be two outputs. Any number of outputs can be there, but there'll be two outputs, O1 and O2, which are going to be compared with T1 and T2. Like our model will already have T1, T2, the target outputs, and our model is going to generate O1 and O2, and we are going to compare it and calculate the errors and going to rectify. So now we are going to discuss everything that we have studied in this session through this example. In this example, we are going to deal with backpropagation also. And in this example is a very good example to understand all the concepts that we have studied till now. Okay. So this is an example showing an artificial neural network. As we can see, there are two inputs, I1, I2. We'll take it as X1, X2 because everywhere we have taken the inputs as X. So don't get confused. It's X1, X2. Then H1, H2 are the hidden layers, the hidden layer 1 and hidden layer 2. That is how we can use the backpropagation over here. And O1 and O2 are the outputs which we will get, and 0.01, 0.99 are the T1 and T2, the target outputs. Like this example over here wants you to give these outputs, 0.01 and 0.99. So these are the X1, X2 values, 0.05, 0.10. These are the two hidden layers. These are the bias factors that are present. So there are two bias factors. One is present between the input and the middle layer, and the other is present between the hidden layer and the output layer. So bias 1 value is 0.35, bias 2 value is 0.60. And all these lines, like I1 is connected, see the representation is still there. I1 is connected to H1, I1 is connected to H2. H1 is connected to O1, H1 is connected to O2. So every node is connected to all the nodes of the next layer. So I1, so these lines over here are the edges of your artificial neural network. And every edge, as I already discussed, has weights. So this edge has W1 weight, W2, W3, W4, W5, and so on with their values. So this is what is mentioned over here. So now we have to calculate the outputs, the O1 and O2. We have to compare what is the basic idea behind it. We have to calculate the outputs. We have to compare the outputs with the target outputs that are given over here 0.01, 0.99. And we have to keep repeating the steps unless our outputs, the actual outputs we got, are not equal to the desired outputs. And once they are equal, means our model has worked efficiently. So we are going to go through whole three major processes which are going to give us the appropriate values so that we can make our model efficient. So we are going to use the back propagation algorithm. Back propagation means we are going to go backwards. So backward propagation of error, that is output to hidden layer. Like we are going to go in this direction. In the single layer neural network, we are going this. Here, we are going to go in this direction. So we are going to calculate all the things related to this question in three parts. First part is going to be our forward error. Like we are going to go, like normally in the case of single layer neural network, how did we calculated the values? We are going to do the same thing. We are going to go in the forward direction. And in the part two, we are going to go to the backward direction, because obviously when we go in the forward direction, we are going to get outputs O1 and O2, which are not going to be equal to the desired outputs. If they are equal, obviously it ends over there. But most probably they are not going to be equal. So when they are not equal, what do we have to do when our outputs are not equal? Only thing we can change is the weights. So we are going to go backwards. Now backwards, the first thing comes is the layer between the output and the middle layer. So this area W5, W6, W7, W8, W8 are going to be changed first. Okay, now we are going to change these weights, and then for the part 3, we are going to change W1, W2, W3, W4. We are going to move in this direction. So let us start the process. So part 1 is calculating the forward propagation error for all the nodes. So now what do we have to calculate? To move in the forward direction, we need to know this. We already know the input values, but we need to know this H1 value, H2 value, this O1 value and O2 value. Now, how do I calculate it? So there are two things associated with every value. For example, when I'm going to calculate H1, I'm going to calculate H1 in and H1 out. Now, what is in and out? I have inserted two arrows in this. Arrow which is going towards the node is the input. Arrow which is going away from the node is the out. So this arrow says H1 in. This arrow says H2 out. So firstly, we are going to calculate H1. Okay, so H1, firstly, we are going to calculate H1 in. Now, this arrow we are going to see H1 in. We are going to move in this direction. So H1 in. Now you see I1 along with W1 is entering H1. I2 along with W2 is entering H1 and bias 1 is entering H1. These three things are entering H1, right? So when I sum it up, I'll get the value of H1. So H1 in is equals to I1 into W1, I2 into W2 and B1. That is the bias factor. So same thing is going to be written over here. H1 in is equals to X1 W1, X2 W2 and B1. X1 W1, X2 W2 and B1. Now when I replace all the values of these, I'm going to get the H1 in. That is in the value of H1 in. Now how do I calculate H1 out? There is a formula to calculate the the outgoing values from the nodes. And the formula is 1 upon 1 plus e raised to power minus net H1. Now what is minus at net H1? H1, that is H1 in only. So 1 upon 1 plus e raised to the power minus H1 in, which we already calculated was 0.37. So when I keep this value 1 upon 1 plus e raised to the power minus 0.377, I get the value 0.5932. So we have calculated H1 in, we have calculated H1 out. So this thing is done. This node is completed. Now we are going to go to the H2 node and we are going to calculate H2 values in a very similar way. So H2 in, if we see H2 in, it is getting I1, W3, I2, W4 and B1 bias factor. H2 is receiving I1, W3, I2, W4 and B1 bias factor. So, sorry. Yeah. So these things are going to be added for H2 in. The X1 W3, X2 W4 and B1 and the H1 in is calculated. And same way, like we calculate H1 out, 1 plus e raised to minus H1 in. Similarly, we calculate it over here. H2 out is, now the formula is going to change, 1 upon 1 plus e raised to the minus H2 out. So H2 out, when we keep, the answer we get is 0.5. And I've already written the values because using calculator and all is very tough over here. Now we are going to calculate H1 and H2 are calculated. Now we are going to go to O1 and O2. So again, same steps. In forward, it is very simple to calculate these things. So O1, sorry, O1 is getting um, H1 W5, H2 W6, and V2. So O1 in is going to get H1 W5, H2. Okay, this out over here mentions because we are going in this direction. Now H1 over here, you will be confused like which H1 to take, in one or out one. But because we are going in this direction, we will take the H1 out. So H1 out into W5, H1 out into, sorry, H2 out into W6. Yeah. H1 out into W5, H2 out into W6 plus V2. And this is the O1 in. Now O1 out, same formula, 1 upon 1 plus e raised to the minus O1 in. So this is the value. Same things we are going to follow for O2. So by this, we have calculated H1, H2. And from this, we have calculated O1, O2. This was the only step we have to do. We had to finally calculate the expected outputs that were O1 and O2. Now, what the values did we got? We have to see O1 out and O2 out. O1 out we got was 0.751 and O2 out we got 0.77. Are these matching with our desired outputs? No. Because desired output was 0.01, we got 0.7, I think 0.7. And here it was 0.99 and we got 0.7. So this is not correct. We need to modify our weights so that we can get the desired output. Now, how do we do that? Now comes the part 2 of the back propagation algorithm, that is modifying weights which are present between the hidden, can be also called a middle and the output layers. That is, we are going to modify W5, W6, W7 and W8. Okay, before that, we have to calculate the net error that we have got. If you look at the values of target obtained, before going to part 3, there is some part missing over here. If we look at the values of target obtained, they are different. Hence, we calculate the error. As we already saw, T and O are different, so we have to calculate the error. Now, what is the error formula? Half into target minus output whole square. So, as there are two outputs, O1 and O2, we are going to calculate errors for O1, we are going to calculate error for O2, and we are going to sum it up. That is our net error that has occurred while going in the forward direction. So O1, EO1 and EO2. So EO1 is what? Half into target O1 minus out O1 whole square. Okay, so half into target O1, that's 0.01, what we had to get. And this is 0.51, what we have placed over here. And we have calculated 0.27. Similarly, we have calculated EO2 and we have calculated the total error. Now, this total error is the error which has occurred over this, over here and over here. So we have summed up the two errors. So this is the E total. Now this is hence the total error without modifying weights. Now we are going to modify the weights and compare the error with the above. That is error reduced or not. Hence, we need to check for different weights and the error will keep on reducing very slowly. So the idea behind this is we have calculated the error. Okay. Now we are going to modify weights by moving in the backward direction. Like we'll first modify W5, W6, W7, W8. Then we are going to modify W1, W2, W3, W4. All the weights are modified. Now again with those weights, we are going to go through the same steps. We are going to, in the forward direction, we are going to calculate the O1 and O2 and again going to calculate the error. So we'll see the previous, like here the error is 0.29, approximately 0.3. The next time the error is going to be reduced from a very small, like here it is 0.98, it will be 0.91 or 0.90. This little modification is only going to happen. So we have to follow 10,000 steps to basically reach till zero error or very less error to make our desired output equals to the output which we have actually got. So these steps are repeated again and again. Hence, we need to check for different, like I modified all the weights, then calculated the E total. It only modified by 0.007. Then again, I'm going to go backwards and change the weights and slowly the procedure is calculated. Now we are going to see how we are going to change the weights going in a backward direction. So backward propagation error. Firstly, we calculated the forward propagation error. Now we are going to calculate the backward propagation error. So first is output layer to hidden layer. As we are going backwards, we are going to go from output to hidden layer. So adjusting weights between the output and hidden layer W5, W6, W7 and W8. We are going to see for W5 and similar process is going to be carried for W5. Sorry, W6, 7 and 8. So how are we modifying W5? We have to calculate the share, the error W5 has created. The error W5 has created in the total error. Like we calculated E total. E total was this error. You have to calculate the share of error W5 has done. So how do I calculate it? E total upon del W5. This is the formula. Now, del E total upon del W5 is equal to del E total upon del out O1 into del out O1 upon del net O1 and del net O1 upon del W5. This formula is there. So this diagram is representing this E total we got and W5, the share of the error share of this W5 is calculated by this formula. Now what will we do? We'll get this error that was being made by W5 and we are going to change modified W5 star is a modified W5. So modified W5 is going to be equal to W5 plus eta del E total by del W5 and eta is the learning rate. So this is the formula which we are going to finally follow to modify our W5. Okay. So now we have to calculate these three functions, multiply them together, and we are going to get this E total upon del 5. So first function is del E total upon del out O1. So what is the formula of E total? This is the formula. This is O1 error and this is for the O2 error. So when we add these two, we are going to get 2 times of half target O1 minus O2. And there's the final formula what we are going to get after differentiating is minus target O1 minus out O1. Minus of target O1 minus out O1. So what is target output 1? Target output 1 was 0.01. So we have placed 0.01 over here and out of O1. What was out of O1 we already calculated. O1 over here we have calculated. Out of O1 is 0.751. So we are going to place over here 0.75. And the answer is 0.741. Similarly, we are going to calculate this function del of out O1 upon del of net O1. So del of out O1 is what? 1 upon 1 plus e raised to the minus net O1. When we differentiate it, we get this out O1 upon 1 minus out O1. These terms are very complicated, but it's not that difficult. Like once we sit and do this. So out O1 is again 0.751 and 1 minus out O1 is 1 minus 0.751, which is finally calculated and the answer is 0.186. Now to calculate the last thing, del net O1 and del upon del W5. So del net O1 upon del W5 is what? What is net O1? Net O1 is, yes, O1 over here. Net O1 is H1 into W5, H2 into W6 plus B2. So this is your net O1. Net O1 is W5 into output H1, W6 output H1, B2. So when we differentiate it with respect to W, what happens is this term is constant term. There is no W5. So this is 0. This term is also 0. And over here, W5 is the is what we are differentiating with. So output H1 is the final result. So this results into output H1. And output H1 was 0.5932. That is 0.6. So we are going to place 0.5932. Now finally, we have to calculate del E total upon del W5. So we are going to keep these three terms together, which is 0.741 into 0.186 into 0.59. And finally, we'll get the result as 0.0821. So this was the del E total upon del W5. Okay, now we have to modify W5. W5 star is W5 plus eta into del E. Eta over here in this question, consider it as 0.5. So see, W5 star is equals to W5 minus eta star del E total del W5 is equals to 0.4. W5 in actual was 0.4 minus eta is 0.5 what we have considered and into this Delhi total upon del W5. What we have calculated is 0.0821. So we have put it and the result is 0.3589. So this is how we have modified the W5 value. Similarly, we can modify W6, W7, W8, or like all the methods will are not mentioned, but we can modify the sixth, seventh, and eighth weights in a similar manner. Now we have modified, we have calculated forward propagation error. Now we have modified the weights W5, W6, W7, W8. Now it's the time to modify W1, W2, W3, W4. So we move further to the part 3, which is saying calculating backward propagation of error, calculating W1, W2, W3, and W4. So again, we have to use the same formula, del E total upon del W5. Similarly, over here, del E total upon del W1. This is equal to del E total. Now, these two terms are similar to what we uh, discussed previously, but this is changing. This is now del E total upon del output H1. This is the same diagram. Yeah. So del E total upon del output H1 is not a single term because it is again a combination of two terms. Del E total del output H1 is del E O1, del E output H1, and del E O2 output H2. Okay, H1. Because we are differentiating with respect to H1 only, but the errors are being divided. So del E O1 is again segregated del E O1 upon del net O1, del net O1 upon del out H1, and similarly this is done through this. So this entire function, the first function is calculated with this formula. First we'll calculate del E O1 upon del net O1, which is equals to this del E O1 upon del del out O1 into del out O1 upon del net O1. So del E O1 upon del out O1 we have already calculated. Del E O1 upon del out O1. So this was 0.741. So we kept 0.741. And del out O1 upon del net O1 again we have calculated, which was over here. Del out O1 upon del net O1, that is 0.186. So we put this and we get the value. Then for the next function, del net O1 upon del out O1. Again, del net O1. O1 function, we can calculate O1 function. What is O1? H1 W5, H2 W6, and B2. So O1 is H5 W H1 W5, H2 W6, and B2. And we differentiate it and get W5 because these are constants. And finally, we have to multiply these values, this into this, and this is the result. Similarly, we calculate del O2 upon del output H1, and finally the total, this term is calculated. This del E total upon del out H1 is calculated through this formula. Now these two are again same, del output H1 upon del net H1, del net H1 upon this. So del output H1 is this. We differentiate it and we get this. And similarly, this the other term. Now for calculating the net, we calculate it as this is what we got over here, 0.036 first term. Second term we got 0.24 second term, and third term was 0.05. So this was the the iteration, the change what we have got for the error change what we have got for W1. So we are going to modify W1. W1 starts with W1 minus eta into del E by del W1. That is W1 over here. You can see is 0.15. So W1 is 0.15, eta is 0.5, and del E total upon del W1 is 0.004. So the value calculated is 0.14, right? This method can be used to update 2, 3, 4. Now we have updated the values of W5, W6, W7, W8, W1, W2, W3, W4. Now what happens? What is the conclusion? We have updated all our weights. When we fed forward the 0.05 and 0.1 inputs originally, the error on the network was this. So firstly, in the forward propagation, if we see, the total error was 0.29. So total error was 0.29. After this first round of back propagation, the total error is now down to 0.912. As we have calculated the total error, Okay, so we have updated the weights. Now we do the same procedure of going forward with the updated weights, and we calculate the new error. So when we calculate the new error, it is 0.291, and here it is 0.298. The first error was 0.298. This was 0.29. Only 0.007 difference came. So on the first iteration, the changes, we got only 0.07 improvement in our modeling, improvement in the output, which means it may take 10,000 steps for us to rectify and for us to make our model reach to the desired output. For example, the error reaches to 0.00035. At this point, when we fed forward 0.05 and 0.1, the two outputs neurons generates this versus 0.1 target and this versus 0.99 target. So this happens after 10,000 steps. What the O is 0.015 and what we desired was 0.1, which is approximately similar, and 0.9 and 0.9. So this happens after 10,000 steps. So this is all about backpropagation algorithm. I hope it was clear. And these are certain remarks on backpropagation. Uh, with this slide, we are going to wind it up. Um, so quickly, we are going to discuss these remarks. Convergence and local minima. Backpropagation allows for change. Hence, convergence means every node is interconnected. That is the information passed through all. As I already told you, every node in a previous layer is going to be connected to the node in the all the node in the next layer because all information has to be passed on. Second is representational power of feed-forward networks. Detailed or effective representation of network depends on width and depth. Width means like the number of layers that are present, and depth means the number of nodes present in all the lips. Okay, so representation can be done in different functions. Then hidden layer representation, by using backpropagation, we can introduce new features in the hidden layer which are not explicitly present in the input list. So what happens is even the hidden layer is the most powerful layer of this ANN. We can even modify the hidden layer. We can add some new features to it. Like without changing the input, we can get the desired output by doing some changes in the hidden layer. And generalization, overfitting, and stopping criterion. So when to stop the algorithm and when the error is smaller below the threshold value, we need to stop the algorithm. So we discussed some basic terms of ANN, and we also discussed the backpropagation algorithm for multi-layer neuron. A single layer neuron can be used for linearly separable data, and multi-layer neuron is used for non-linearly separable data, which is done by the backpropagation algorithm. So we could have discussed this example of face recognition, but I think that's all. Um, so the ANN can be like this, the application of ANN, face recognition. So that's all. Thank you so much. Thanks for joining in. Thank you.